Hello, am I audible?
Yes.
Yes.
Okay. Can you see my screen?
Yes.
Okay. So today we will see how can we regularize models so that we can prevent overfitting, right? So we will regularize models and most commonly used regularizations are the L1 regularization and the L2 regularization, right? Yes. So here we will see linear model. So how can we regularize linear model? But yes, we can also regularize non-linear models also, right? So deep learning model. So in fact, any machine learning model you can regularize, right? And we will see here three types of regularization: ridge, lasso, and elastic net. So here, yes, L1, L2 norm I have already discussed, right? So previous session I discussed L1 and L2 norm, right? So in ridge and lasso we will use, so only the difference is we will use L1 norm or L2 norm, right? So L1 norm means absolute value we are taking. L2 norm means we are taking square value, right? So if we are taking absolute values, then we are calculating mean absolute error. If we calculate absolute error, mean absolute error, we will calculate absolute values, right? Yes. So computing sum of absolutes corresponds to L1 norm, right? So here for L1 we will write here 1. So 1 means we are taking absolute values, right? And L2 means we are taking square value, right? So root mean computing the root of a sum of squares corresponds to L2 norm, right? So for L2 we will write here 2, right? So L2 norm also called Euclidean norm, right? And this is the general formula for LK norm, right? Yes. Okay. So now let's start. So first we will see ridge regression. So in ridge regression, we will use L2 norm, right? So ridge regression is a regularized version of linear regression, right? So linear regression plus we are doing here something extra, right? So we are also using regularization. And here what type of regularization we are using? We are using L2 regularization. Why 2? Because here we are using squared, right? Theta I square we are using. And here in the summation, uh, we are using I is equal to 1 to n, right? So which means theta 0 we are not considering. So bias term we are not considering, and we are considering all other remaining terms, right? So theta 1, theta 2, theta 3, all terms we are including here in this summation, right? And this regularization term we will add to the cost function, right? Now cost function can be any function. So cost function can be RMSE error, right? Or yes. So or depending upon what type of problem we are solving, right? So if we are solving classification problem or regression problem, then we will have one cost function. So we will add one more term, this regularization term, to the cost function. Okay, so let's take one example. So suppose we are given this type of data points. These types of data points we already have, right? Now we want to fit a we want to fit a we, we want to fit a polynomial, or let's say line, uh, for these given data points, right? Yes. So for that, what we will do, we will fit here several polynomials. So degree zero polynomial, or degree zero polynomial means the constant line, right? Or degree one polynomial means straight line, right? Degree two polynomial, degree three polynomial. So like that, we have several polynomials. So we can fit, let's say here we are fitting degree 10 polynomial, right? So now this degree 10 polynomial has high degree of freedom, right? Because this 10-degree polynomial can bend several times, right? So this 10-degree polynomial can bend several times, as you can see here, right? So since this 10-degree polynomial has a high degree of freedom, or in other word, it is this 10-degree polynomial is so flexible that it can fit each and every data points, right? So error, very low error, right? So if we use a very high degree polynomial for this type of data point, then overfitting may be there, right? Now to prevent that, we will use here regularization, right? Now what this regularization will do? Uh, Regularization will penalize coefficient of this polynomial, right? So if regularization penalize coefficient of this polynomial, which means now this graph becomes smooth, right? Because higher degree coefficient it will penalize, right? Yes. Okay. Yes. So we have some cost function. Cost function can be any function. So it can be mean square error, or right. So in cost function, let's say MAC error we are taking, right? Plus we also add one more term, regularization term, right? Now let's say we are doing linear regression problem, right? So model can be y is equal to theta 0 plus theta 1 time x1 theta 2 x2, or let's say we are fitting a polynomial, right? So in that case, and assume we are using only one feature, right? So for the sake of simplicity, we are assuming in input we are only having one feature, right? So one feature x1, and we are fitting here, let's say 5-degree polynomial, right? So here this y will be theta 0 theta 1 x1 plus theta 2 x1 square theta 3 x1 cube and theta 4 x1 power 4. Okay, so assume we are fitting here a degree 4 polynomial, right? So degree 4 polynomial we are fitting, and in the input we are only having one feature x1, right? And let's say data points you are having something like, so suppose these are the data points that you want to fit a polynomial, right? Yes. Okay. So here, if you fit a 4-degree polynomial, 4-degree polynomial has a high degree of freedom as compared to 2-degree polynomial, right? Because 4-degree polynomial can bend more number of time, right? So it very easily it can fit the training data very well, right? Okay. So in that case, the MAC error, the training error will be less, but at the same time, validation error will be high, right? Because that model is not generalizable because of overfitting problem, right? And we want to avoid that overfitting problem, right? So for that, what we can do here, we can add here regularization, right? Now the regularization can be L1 regularization or L2 regularization. So suppose if you are using L1 regularization, then here in regularization term, we will add theta 1, we will add absolute values. We will add here L1 norm, right? So theta 1 absolute, theta 2 plus theta 3 plus theta 4, right? So in L1 regularization, we will add these absolute term here, right? In L2 regularization, here we will use square term, right? Theta 1 square plus theta 2 square plus theta 3 square plus theta 4 square, right? So if we are adding square term, then this type of regulation is called the L2 regularization, right? Okay. And yes, so now we want to minimize this total term. Total term is MAC plus R, right? If we are regularizing, um, let's say if we are optimizing unregularized cost function, then we will only have MAC. But since we are here regularizing, we are optimizing regularized cost function. So now we will have MAC or the cost function plus one more term, regularization term, right? Okay. So if you fit here, let's say a high degree polynomial, can fit these data points very well, right? So in that case, MAC error will be low, right? Okay. So in L1 and also in L2, in both cases, what exactly we are doing here? We are adding magnitude of uh, these theta 1, theta 2, theta 3, theta 4 magnitudes we are adding in some form, right? In L1, we are adding in absolute form. In L2, we are adding in square form, right? But in we are adding some uh, these unknown magnitude of these unknown parameters in here in some form, right? Okay. So if you fit here degree 4 polynomial, then this MAC, this first term will be low, right? So maybe let's say you are getting one MAC error, right? One MAC error you are getting if you use here degree 4 polynomial, right? But let's say at the same time, let's say if since you are using degree 4 polynomial, so the second term will be high, right? Okay. So the second term will be high. So let's say the second term or this regularization term is, let's say 1. So total value, you will get 2, right? Now let's say if let's say in other case, let's say if your regularization or optimization is optimizing in such a way, let's say this theta 3, theta 4 becomes 0, right? Theta 3 is 0, theta 4 0. In other words, you are fitting here a quadratic polynomial, right? So in that case, let's say error is now 1.5, and let's say since theta 3, theta 4 becomes 0, so only you are left with theta 1, theta 2. So maybe let's say you are getting these values as 0.2, right? So total you will get 1.7, right? The other case, let's say when all these theta are 0, let's say theta 1 is 0, theta 2 is 0, theta 3 and theta 4 all are 0. In that case, what will happen? this magnitude term will become 0, right? Because all thetas are 0, but then this error will increase, right? So maybe you will get here, let's say, a very high error 5. So total you will get 5 value, right? Now what we want exactly? We want the sum to be minimum, right? So here what value we will pick? We will pick 1.7 value, right? Which means what exactly we are doing here? We are giving weightage to this first term, MSE term, and also we are giving some weightage to this regularization term, right? So which means, let's say uh, uh, if we have overfitting in our model, let's say if we are having overfitting in model, in case of overfitting, this first term will be very less, right? MSE error will be very less because the model can fit because now the model can fit these training data points perfectly, right? So which means the error will be very less, right? So for example, this case we are only getting one error, right? But then the regularization term, the second term will increase, right? Because if you want to fit each and every data points, then we should use very high degree polynomial, which means we will have several theta's values. So therefore, this absolute sum or this squared sum will increase, which means the second term will increase, right? So if this error is less means we are using highly complicated model, then in that case, this square term sum of this L1 norm or L2 norm will increase, right? Or in other word, if we are highly penalize these theta values, in that case, the second term, this regularization term will become very small, but then the MSE error will increase, right? So let's take uh, in case here. So let's say if theta 1 0, theta 2 0, theta 3 0, theta 4 0. So what we will finally get y is equal to theta 0. So y is equal to theta 0 is nothing but a line parallel to x-axis, right? So in that case, we will have a very high MSE error. So this case, right? We will have a very high MSE error, but the second term is 0 because in that case all theta values are 0, right? So in regularization, we will get this type of solution where we will have uh, uh, some MSE error and we will have some regularization term, right? So any doubt in this example? So what should be the model in this case if you want to fit this type of data point? What optimizer will do? Optimizer uh, will will make theta 3 nearly equal to 0, theta 4 nearly equal to 0, because for this type of data points, we can fit a quadratic curve, right? Degree 2 polynomial we can fit, right? Any doubt here in this example? Hello, am I audible?
Yeah, you are. No questions.
Okay,
Thanks.
okay. Now sometimes what we can do, we can use here a regularization constant. So let's say lambda. Lambda is a regularization constant, and using this lambda, we can trade off between the cost function and the regularization term, right? So here MSE we are taking as a cost function, right? C theta. And this regularization term also depends on theta in right. So here in regularization term we are having theta values, theta 1, theta 2, theta 3, and theta 4, right? Okay. So if we are here taking, let's say, lambda value very high, which means we are giving more weightage to this regularization term, right? If we use small values for lambda, then we are giving more weightage to first term, right? Because what exactly we want this sum to be minimum, right? MSE plus lambda times regularization, we want to be as low as possible, right? So if in case this lambda is already very small, so let's say if lambda is 10 raised to power minus 6 or 10 raised to power minus 7, then even if this regularization term is high, the lambda times R will be low. So in that case, the optimizer will focus more on MSE part. First term, it will focus more, right? So in case when we have lambda value very small, optimizer will focus on the original cost function, right? If lambda value is very high, then in that case, let's say if lambda is 100 or let's say lambda is 10. So even if this regularization term is low, lambda times R will be high, right? Because lambda is, we are taking here is very high value, right? So if lambda is a high value, in that case, optimizer will focus more on this second term, lambda times R. Because optimizer, what optimizer want to? Optimizer will optimize this combined summation, MSE plus lambda R, right? Yes, and this lambda is called the regularization hyperparameter. And using this regularization hyperparameter lambda, we can trade off between MSE and R, which means what exactly we want. We want more regularization, or we want to do more well on training data, right? If you want to perfectly fit any model on the training data, then we are focusing more on the MSE cost function, right? More on the MSE part. Okay. Yes. So in both L1 and L2, we are having magnitude of these theta values, right? But in case of L1, we are using function of type y is equal to mod x, right? And we already know what is the shape of y is equal to mod x, right? So y is equal to mod x is, yes, V shape function, right? So this is the y is equal to mod x, right? And in L2 norm, we are having function y is equal to x square, because we are using here square term, right? So y is equal to x square also we know. So this is y is equal to x square. Okay, so in both y is equal to mod x or y is equal to x square, the minima is x is equal to 0, right? But here we will get perfectly 0 value, right? In case of, because it's a V-shaped function. It's a V-shaped function, so we will get here perfectly 0 value. In case of y is equal to s square, you will get value very close to 0, right? So you will not get exactly 0, but you will get value very close to 0. So if you use L2 regularization will penalize theta values, but theta values so theta values will become small, but here theta will not be exactly 0, right? Because of shape of this y is equal to x square function, right? But if you use L1 regularization, here it will make these theta values exactly 0. So let's say if theta 3 is not required, theta 4 is not required, the regularization will make these theta 3 exactly 0, theta 4 exactly 0, right? If you use L1 regularization. But if you are using L2 regularization, theta 3, theta 4 will become very small. So let's say theta 3 is nearly equal to 0, theta 4 is nearly equal to 0, but not exactly 0 if you use L2 regulation. L1, if theta 3, theta 4 is not required, it will make theta 3, theta 4 exactly 0, right? Okay. So if you want to create sparsity in your model, or if you want to do feature selection, then we always use L1 regularization, right? Why L1? Because in case of L1, we can have 0 values, right? So let's say if you use L1 regularization, and if theta 3, theta 4 is not required, in that case, theta 3 will be 0, theta 4 will be 0, which means you are only left with theta 0, theta 1, theta 2, right? And these terms we don't have. So if we want to do feature selection, so for example, we don't want cubic feature, we don't want degree 4 feature, then we can use L1 regulation, right? Any doubt here? Okay. Okay. So in ridge regression, we will use L2 regularization, right? So we will use a square term. Okay. So adding a regularization term to the cost function forces the learning algorithm to not only fit the data, but also keep model weights as small as possible, right? Because here we are adding here square of theta I, right? Which means now optimizer will focus on both term. It will focus on MAC part also, and also it will focus on the second term, right? So the second term can only be minimized when these theta values are small, right? Because we want this combined MAC plus alpha time regularization, this J theta, this combined term we want to be as minimum as possible, right? Okay, so now it will focus on it will focus on both MAC part. It will focus, we want here low error, plus at the same time, we also want these theta values to be small, right? Okay, so focus learning algorithm not only the fit the data, but also keep model weight as small as possible, right? And yes, this regularization term we will should only be added to the cost function during training, right? Once the model is trained, we will evaluate model performance using unregularized performance measure, right? Why? Because here using this cost function j theta, we will train our model, right? So we will train our model using regularized laws, right? MAC laws we already have, right? We want MAC error to be as low as possible, plus some regularization, and here alpha is the regularization constant, right? Plus some regularization term. So MAC laws plus regularization term, right? Yes. So using this J theta, now we train our model, right? So what optimizer will do? Optimizer will focus on MAC loss also, plus at the same times this theta the value. It will focus on magnitude of this theta values also, right? So it will penalize theta values, so this theta values will not become too high, will not become will not attain any high value, right? So these theta values, now we have small values for these theta values, plus loss also we have, we will also focus on loss part, MAC part, right? Okay. Yes. So once we know the solution, once we know the theta values, we can use theta values to make prediction, right? So for example, in case of linear regression, what we will do at the test time, we will use theta transpose x, right? So theta transpose x we can use for predictions, right? Theta transpose x, right? So we will only use j theta for the training part, right? So for training, we will use regularized loss function, MAC loss function plus alpha times regularization term, right? And for the test time, we will only use theta value, right? So let's say using this cost function, uh, we obtained optimal value of theta star we are obtaining. So now using that optimal value of theta, we will make prediction at the test time. theta transpose x, right? Yes. So we will add regularization terms only during training time, and test time we will not use regularized, right? So training time we will only use regularization, and test time we will use uh, optimal theta values to make prediction, theta transposition. Yes, this hyperparameter alpha I have already explained, right? So this alpha is a hyperparameter that controls how much weightage you want to give the second term in the overall cost function, right? Because overall cost function is now having two terms: original cost function MSE loss plus alpha time this regularization term, right? So if alpha is zero, which means you are only focusing on the first part. You are only focusing on the MSE loss, right? Which means you are doing you are optimizing a unregularized loss, right? If alpha is equal to zero, right? So this becomes simple linear regression, right? If alpha value is very high, which means you are focusing more on this second term part, right? Because this overall MSE plus alpha times regularization, we want to be edge low, edge possible, right? Yes, and we generally do not include theta zero in calculating L1 or L2 norm, right? So the summation always starts from theta is equal to 1, right? Yes, so this I have already explained, right? In L2 regularization, we will take here square term, right? Okay, this 1 by 2, can anyone answer why I am taking here this 1 by 2 term? Yes, so this MSE theta is let's say is your original cost function C theta, and again this is here we are using some regularization term R that also depends on theta, right? So here the form is C theta plus some regularization constant alpha and R theta by 2. So here I am taking this two term. What will happen, let's say if I remove this two term? Let's say if I optimize C theta plus alpha R theta, then what will happen? Can anyone answer? Okay, so in both cases, you will get same answer, right? Here we are taking this term 2 because let's say when you differentiate this function, this 2 will cancel out, right? So for the sake of simplicity, we are taking here this 2 term, right? Because let's say uh, if you have y is equal to x square, if you differentiate this function with respect to x, what you will get? You will get 2x, right? So we are taking here this 2 terms so that this 2 and 2 will cancel out, right? So for simplification purpose, we are taking here, right? But even if you remove this term 2, you will get the same solution, right? Because here we are using this parameter alpha, right? So alpha this alpha you can take any value, right? You can increase this alpha value, you can decrease this alpha value, right? If you want to give more weightage to this regularization term, we will increase alpha value. If you want to give more weightage to this first term, C theta, cost function, then we will decrease alpha value, right? Yes. So here in ridge regression, we are taking we are taking here L2 norm, right? Yes. And Yes. So before performing rich regression, we will always do feature scaling, right? So for feature scaling, we can use a standard scaler, right? So we will first do feature scaling and then we will do regression. We will do ridge regression because ridge regression is sensitive to the scale of input. If all feature values are not on the same scale, then it will create problems in optimization, right? So we will first do feature scaling, and then we will do the ridge regression, right? Okay. So now let's train model using ridge regression on some linear data using different alpha values, right? So here uh, these blue points are our data points, right? And in input, we are only having one feature x1, and y is our output, right? So we are predicting real valued output y given input x1. So in input, we are only having one feature, right? Okay. So here, let's say if we are fitting a 10-degree polynomial, 10th degree polynomial we are fitting here, and we are taking here alpha is equal to, we are varying alpha values, right? So as I said, if you increase alpha value, it will give more weightage to this regularization term. So if you increase alpha value, it will penalize theta values, right? Um, and if you decrease alpha value, it will focus more on this first term, right? Okay. So here we are fitting here 10-degree polynomial, right? And here we are taking three alpha values. Alpha is equal to 0. Alpha is equal to 0 means we now we are not using regularization term, right? Because regularization term will vanish if we use alpha is equal to 0, right? Which means we are optimizing unregularized loss function, right? Yes. So alpha is equal to 0. If alpha is equal to 0, which means we are not using regularization at all. So in case of alpha is equal to 0, you will get this curve, right? And as you can see, since we are fitting a degree 10 polynomial, so here in this case the overfitting will be there, right? Because we are fitting each and every data points, right? And this 10-degree polynomial can bend 9 times, so it has a high degree of freedom. So therefore, it will fit data points. Okay. Now, in case of very high value of this alpha is equal to 1 means we are focusing more on this regularization term, right? So if you use here very high value of alpha, then it will penalize these theta values very hardly, right? So if alpha is a high value, then this regularization term will be high, right? So which means, and now optimizer will penalize these theta values hardly, and these theta values will become very small, right? So even if you use 10-degree polynomial, since all theta values will become very small, which means you end up getting a linear model, right? So this is a very simple model you will get when you use very high value for alpha, right? Because all high degree coefficient will become 0, right? Okay. If you choose alpha a moderate value, suppose 10 raised to power minus 5, now you will get a smooth graph, right? Because you are focusing on both the MSE part plus as well as the regularization part, right? Okay, any doubt in this example? Yes, increasing alpha means you are giving more weightage on the regulation part. So it will penalize theta values very hard. So theta values will become very small, right? If we use high value of alpha, right? So it is also you can also verify this fact from this graph, right? In case of alpha is equal to 1, the polynomial become simple, right? Because alpha values will become now 0. So even if we use a 10-degree polynomial, the high degree coefficient term will become 0, right? Higher degree coefficient term will become 0, right? Okay, so let me ask one question. So suppose if you are using a very high degree polynomial, which means you are using a complicated model. You are using a complex model. If we use a very high degree polynomial. Suppose if you want to decrease model complexity, then should I increase alpha value or should I decrease alpha value? If I want to increase model complexity. So can I control model complexity using this alpha value?
Yes.
Yes. So what will happen if I increase alpha value? It will penalize coefficients. This theta values it will penalize more, right? Which means model complexity will decrease, right? Model complexity will decrease.
How long we can increase or decrease alpha value?
So any value we can take. So alpha is a hyperparameter, and alpha can take any value, right? So let's say theta 1 x1, theta 1 or theta 2 x1 square, theta 1 x1 cube, sorry, theta 3 x1 cube, right? Okay. So if alpha value is very high, or let's say if you increase alpha value, this theta value will become very small, which means you are decreasing model complexity, right? Because let's say if theta 2 is very small, theta 3 is very small, then you end up getting model something like this: y is equal to theta 0 plus theta 1 x1, which means model complexity will decrease. Model complexity will decrease when you increase alpha value. But if you decrease alpha value, then these theta 1, theta 2, theta 3 will now will have some values. So in that case, model complexity will increase, right? So you can control model complexity using this hyperparameter alpha, right? If you increase alpha value, model complexity will decrease. If you decrease alpha value, model complexity will increase, right? Which means you can control overfitting, underfitting using this alpha value, right? If we have overfitting in our model, then how can we prevent overfitting? We can prevent overfitting by reducing model complexity, right? So we have to reduce model complexity. So in that case, if we are suffering from overfitting problem, then we will increase alpha value, right? So if we increase alpha value, model complexity will decrease and overfitting problem will solve, right? If we are having underfitting in our data, then we will increase alpha value, right? To increase model complexity. Yes. Now this combined loss function MAC plus alpha times this regularization, we can solve either using closed form solution, or we can use gradient descent, right? So I've already discussed closed form solution and gradient descent. You can use any method to solve this cost function j theta, right? The only difference is now we have one more extra term, regularization term. Yes. So if you use closed form solution, then in that case the solution will be this: theta hat is equal to x transpose x plus alpha times a inverse x transpose y. So now since you are using regularized loss function, you have added a regularization term. So therefore, we are getting here one more extra term alpha times a, right? In previous case, this second term alpha time a is not there, right? So we are getting this term alpha a because now we have added one more extra term, a regularization term, right? Okay, so this a is the identity matrix of size n by n, right? N by n. So identity matrix we already know, right? So identity matrix of size n is will have one values on the diagonal element, and off diagonal element values will be 0, right? So A is a identity matrix of size n by n, and this alpha is a constant that we are using in regularization, right? So here we are using one hyperparameter alpha regularization hyperparameter. So this alpha we will use here in this solution, right? Okay, so this solution is called the closed form solution because directly using this formula we can get the optimal value of theta value, right? Okay, so if you want to use the closed form solution, then you will import ridge from this scikit-learn package, scikit-learn.linear. You will import ridge, and then you will fit your data, and for prediction you will use predict function, right? Okay, so here this alpha value you can choose any value for alpha. So alpha is nothing but this regularization hyperparameter, right? So if you are taking alpha value 1, then you will write here alpha is equal to 1. And this solver is so here you will use any solver. So solver means how do you want to solve this equation, right? Because if you want to solve a system of linear equation, there are several methods. So you can think this is one method. So and this random seed we will use for reproducibility, right? Okay, so this parameter you have to mention here alpha, right? What regularization you want? You want high regularization or you want low regularization? So depending on high or low regularization, what you want, you will mention here some alpha value, and accordingly it will give you the solution, right? And let's say if you want to make predictions, you will use this predict function to get the prediction value, right? So if you want to use closed form solution, you will import ridge from scikit-learn. And if you want to use iterative method, SGT method, if you want to use, then you will use SGT regression. SGT regression I've already discussed. The only difference here is we will use here penalty. So if you want to use L1 regularization, you will write here penalty is equal to L1. If you want to use L2 regularization, you will write here penalty is equal to L2, right? Yes. So in case of L1 regularization, we will write here L1, right? In case of L2 regularization, we will write here penalty is equal to L2. Yes, and the same for prediction, we will use dot predict method, right? Okay. Now let's discuss lasso regression. In lasso, we will do exactly same. The only difference is here we will use L1 norm, right? So here, as you can see, we are having MAC loss plus alpha times regularization term, right? So in regularization, we are taking absolute values, right? Yes. So this type of regression is called the lasso regression. Okay. So now let's train model using different alpha values, right? So here also, if you increase alpha value, you are doing more regularization. If you decrease alpha values, you are more focusing on this first term MAC, right? So same concept also apply here. The only difference is here we will take absolute values, right? And since here we are using absolute values, so therefore now this theta values can have zero values, perfectly zero values, right? So that's why we can also use this type of regularization, lasso regression, if you want to do feature selection, right? Yes. So nothing special in this graph. I've already discussed. If you increase alpha value, the graph will become more and more smooth because it will penalize. It will penalize high degree coefficients, right? Coefficient high degree it will penalize. If you use low value for alpha, which means it will focus more on this first term MSE part, right? If you use high value of alpha, then it will focus more on the second term. So it will now the theta I will become smaller, right? If you use high alpha value, right? So same fact you can verify from this figure, right? Here we are fitting 10th degree polynomial. So if alpha is equal to 0 means this 10 degree polynomial can bend several times, right? If you use high value of alpha, then the higher degree term, so let's say x power 8, x power 9, so these terms will become very small because it will penalize these terms, right? Okay, so this slide I have already discussed, right? If you use L1 normalization, then we can do feature selection, right? It will eliminate least important features, right? Because in case of L1, theta can have perfectly zero value, right? So lasso regression we can use to do the feature selection, right? If feature is not required, the corresponding coefficient will be zero, right? So it will lasso regression outputs a sparse model, a model where we are having less number of parameters, right? So let's say in originally we are having, let's say, 5 parameters: theta 0, theta 1, theta 2, theta 3, theta 4. And let's say if theta 3 and theta 4 are not required, then the 3, theta 4 will have zero values, right? If you use lasso regression, because in case of lasso regression, we will use L1, and L1 can make theta 3, theta 4 perfectly zero, right? So now we are having model with less number of parameters: theta 0, theta 1, and theta 2. Theta 3, theta 4 will not be there, right? Yes, so this slide I have already explained, right? So if this alpha value is 10 raised to power minus 7, a small value we are taking, then it will penalize high degree polynomial features, right? No. If alpha value is 1, then it will penalize high degree polynomial features. If alpha value is 0, then it will not use regularization. If alpha value is moderate value, let's say 10 raised to power minus 7, then we will get a smooth graph, right? Because uh, now it will focus on both term, right? The original MSE function, MSE loss plus regularized. It will focus more on it will focus both on MSE loss as well as on the regularization term, right? Yes. So in Lasso here we will import Lasso. So from scikit-learn.linear model we will import Lasso, and here we will mention this this alpha parameter value, right? So if you want alpha to be 0.1, you will write here alpha is equal to 0.1. And what is this alpha? Alpha is nothing but this uh, regularization hyperparameter, right? What weightage we want to give to this regularization term, right? And for prediction, we will use predict method, right? Okay. So now let's discuss this elastic net. Elastic net is nothing but a combination of L1 and L2, right? So elastic net is you can think a between ridge and lasso regression, because in elastic net we will have both L1 regularization term and L2 regularization term, right? So this first term we are having from lasso regularization term. Second term we are having from ridge regression, right? We are having L1 norm regularization also and L2 regulation also. So it's a mix of ridge and lasso regression. Okay.
This
Yes.
R, what is this R value?
So here in case of elastic, we are having two hyperparameter, alpha hyperparameter and R hyperparameter, right? So alpha parameter here we are using to give weightage to this regularization term, right? And R hyperparameter we are using to trade off between L1 and L2, right? So let's say if you want only L1, you do not want L2, then we will use R is equal to 1, right? R is equal to 1. If you want to use only L2, we do not want to use L1, then we will use R is equal to 0, right? So if you use R is equal to 0, this second term will vanish. If you use R is equal to 1, this third term will vanish, right? So this R hyperparameter, using this R hyperparameter, you can trade off between L1 and L2. And using this alpha hyperparameter, you can trade off between the original cost function plus regularization term. If you want to trade off between original cost function plus regularization term, then you will vary alpha value. If you want to trade off between L1 and L2, you will vary R, right? Okay. So when R is equal to 0, it will become ridge regression. And if R is equal to 1, it will become lasso regression. If you want both, then you will choose any value other than 0 and 1, right? So R can have any value between 0 and 1, right? Okay, so when should we use linear regression or ridge regression or elastic regression? So generally, you can use elastic regression, because in elastic regression, we have both L1 and L2, right? Okay. And it also depends on our what type of problem we are solving, and let's say what so let's say if we want to do feature selection, if we want to select if we want to remove unwanted features, then we will use L1 regression, because L1 regularization, using L1 regression we can do feature selection, right? Yes. So in general, we will always use some regularization. Either we will use L1, L2, or we will use elastic, right? But as I said, if we only want some features, we do not want all features, then we will use lasso regression or elastic net we will use, right? Because in both lasso and elastic, we are having absolute term. We are having absolute term. So therefore, we can make unwanted features perfectly 0, right? Because here also we are having absolute norm, right? We are using L1 norm. So we can remove unwanted thetas, right? Yeah. So in general, elastic net is preferred over lasso. And lasso may behave. So we will not use lasso when the number of features is greater than the number of training instances, or let's say when several features are strongly correlated, right? Because in case of lasso, it will make theta values perfectly 0, right? So now it will create a problem. Yes. So elastic net, if you want to use, you will import scikit-learn.linear linear model. You will import elastic net, and here you will mention two hyperparameter, alpha and this ratio, L1 ratio, right? This is nothing but this R, right? So we have two hyperparameter, alpha and R. So we will mention these values, alpha and R, and it will it will apply that regularization, right? And again, for the prediction, you will use this predict method, right? Any doubt in this example? And this random state we are using for reproducibility, right? Okay. Okay, so let's take a 5-minute break, and then we will start uh, early stopping. And again, this early stopping we will use to prevent overfitting, right? So there are several methods to prevent overfitting. Regularization we can use. In regulation also we have several methods, L1, L2, right? We have some other methods. Early stopping is one method to prevent overfitting, right? So this early stopping we will discuss after break, right? Okay, so let's start. Am I audible?
Yes, sir.
Okay. So as I said, early stopping is again a different technique to prevent overfitting. As the name suggests, in early stopping, we will stop early, right? So we will stop early to prevent overfitting, right? So let's take this example. Here, assume we are training some model. We are using iterative methods. And iterative methods, we will use several iterations, several epochs to optimize our model. So assume here we are using 500 epochs to train our model, right? And let's say this y-axis side, we are having RMS error, and x-axis side we are having epochs, number of epochs, right? So initially, since we are starting from random initialization, so initially the validation error will be high and the training error will be high, right? So both train and test or both train and validation error will be high because we have started from random initialization, right? Now, as you train your model more and more, the training error will reduce, and at the same time, validation error will reduce, right? And after some time, let's say you are getting a decent validation error and the good RMS error, right? Now, if we have overfitting in our model, if let's say if overfitting is happening in our in our training in our model, then what will happen? The training error will reduce, right? Training error will further reduce because now in case of overfitting, model will memorize everything. Model will fit the noise present in data. Model will memorize every pattern, each and every pattern present in the data, so that it can perfectly fit the data, right? So training error will become very small, but the validation error now will start increasing, right? So if this type of phenomena is happening in our model, which means model is suffering from overfitting problem. Overfitting problem is the low training error and the high validation error, or the high test error, right? Okay. So as you can see here, when we are overtraining our model, then model may memorize each and every pattern present in the data. Model may learn the noise present in the data if we overtrain our model, right? Which means ideally we should stop at this roughly at 220 or 230 epoch, right? Then we will get the best model. So if we want to prevent overfitting, then what we will do, we will stop early. We will stop at this 220 epoch, and we will not go up to 500 epoch. And this method is called the early stopping, right? Okay, so any doubt in this method? Okay. Yes. So early stopping is a different way to regularize iterative learning algorithm such as gradient descent. And as I said, we will stop early if we are using early stopping method, right? So this is the best model. Okay, so now let me ask one question. How can we find, how can we calculate this, how can we obtain this best model? Okay, so what you can do in each epoch, you can calculate what is the RMSE error, what is the training error, and you can store these three things. You can store, let's say, at you are at epoch 100. So at epoch 100, you will calculate validation error, you will calculate training error, and you will store model that you have at the 100 epoch, right? Now at epoch 101, again you will do the same thing. You will calculate validation error, you will calculate the training error, and you will store the model that you have at the 101 epoch, right? So likewise, in each epoch, you will calculate validation error, training error, and you will store that model, right? If validation error, let's say, is not decreasing further, and validation error, let's say, after certain epoch is let's say is starts increasing, then you will stop at that point, and that is your that model is your the best model, right? Or what you can do, you can train your model from 0 to 500 epochs, and in each epoch you will calculate validation error, training error, and the corresponding model, right? Now you already have data for all validation validation data you already have, right? RMS error for validation data you already have for each epoch, right? You will select the model that for which you have the lowest validation error, right? So this is the epoch where we are having lowest validation error, right? If you go uh, uh, on either side of this point, let's say if you are going left hand side or if you are going right hand side, the validation error is increasing, right? Only for this point you are having lowest validation error. So you will pick the model that for which you are having the lowest validation error, right? Okay, so any doubt in this method, early stopping? Okay, yes. So this slide I have already discussed, right? Initially, since we are starting from scratch, we are initializing model parameters from scratch. So both validation and training error will be high, right? And let's say if you are overtraining your model, then validation error will start increasing, because now your model will learn the noise present in your data, right? So it will overfit your model if you overtrain your model, right? Yes. So we will stop at this point, right? We will stop early. Yes. So this slide I already discussed, right? Okay. Okay. So now let's start logistic regression. Yes. So logistic regression is again a classification problem. So here we are solving a binary classification, right? So don't confuse with this name regression, right? So regression, we will predict a real valued output. In logistic regression, we do the binary classification task, right? So logistic regression is not a regression problem. Logistic regression is a binary classification problem, right? So don't confuse with this term regression, because here in the name we are having regression, right? So regression, we always predict real valued output, but in logistic regression is a binary classification problem, right? Okay, so logistic regression is a binary classifier, and in logistic regression we will estimate probability that an instance belongs to a particular class, right? Okay, so logistic regression will give the probability, right? So for example, let's say if we are having a binary classification problem, let's say positive class or negative class, or let's say, yes, positive class or negative class. So if sample belongs to positive class, then the probability will be greater than 50%, greater than 0.5. If probability is less than 0.5, which means the instance belongs to the other class, right? Okay, and the example is example, you can take any binary classification problem, right? So for example, whether a given email is a spam or not a spam, right? So spam versus not spam is a binary classification problem, right? So if a given email belongs to spam category, then probability will be more than 50%. If probability is less than 50%, then it is not a spam mail, right? Yes. And here for the positive class, either you can take 1 or 0, so 1 or 0, or you can also take 1 and -1, right? So for positive class, you can take 1, negative class, you can take -1, or for positive class, you can take 1, and for the negative class, you can take 0. Okay. So now let's discuss how can we estimate probabilities, right? Because in logistic regression, it's a probabilistic classifier. It always returns probability, and probability we know always ranges from 0 to 1, right? So if probability is having value more than 0.5, which means positive class, else negative class, right? Okay. So just like linear regression, a logistic regression computes a sum of input features plus bias. So here also we will calculate theta transpose x, right? What is this theta transpose x? Theta transpose x is nothing but the theta 0 plus theta 1 x1 plus theta 2 x2, right? So we are calculating linear combination of input features, right? Theta 0 plus theta 1 x1, theta 2 x2 plus theta 3 x3, and so on, right? So in logistic also we will calculate weighted sum of input features. Theta transpose x we will calculate. And unlike linear regression, in case of logistic regression, model output the logistic of result, right? Model output logistic of result. So the sigma function is called the logistic or sigma, right? So the sigmoid function, the sigma is called the sigmoid function or the logistic function, right? So since here in this method we are using logistic function, so that's why this method is called the logistic regression, right? Okay. Yes. So theta transpose x, the same we will do in linear regression. Here the only difference is we will use this sigmoid function sigma. Okay. And what this sigmoid function will do? Sigmoid function will convert any value between 0 and 1, right? So this is the form of sigmoid function. Sigma t is equal to 1 divided by 1 plus e power minus t, right? So this is the formula of sigmoid function, and this t can have any value, right? So t can be positive value, t can have negative value, right? And this is the output sigma t. So as you can see here, the sigma function will always return value between 0 and 1, right? So minimum value here is 0, and the maximum value here is maximum value can be possible here is 1, which means if you take any value, if you feed any value here in the sigma function is an input, and output you will get you will always get value between 0 and 1, which means in output you will get some probabilities, right? Okay. And for t is equal to 0, you will get 0.5 as an output. If you put here t is equal to 0, what value you will get here? 0.5, right? So 0.5 is the threshold value. So if this output value 0.5 is greater than 0.5, or this probability is greater than 0.5, which means the positive class. If output value is less than 0.5, or the probability is less than 0.5, which means the negative class, right? Okay. So since here we are using the sigmoid function, so therefore in output we will get probability, right? So unlike linear regression, logistic regression model outputs the sigmoid of result, sigmoid of theta transpose x, right? But here also we will use theta transpose x, right? Weighted sum of input features, theta transpose x we will use. Okay. Yes. So this slide I have already explained, right? If output probability is less than 0.5, which means the negative class or the label is 0. if output is output probability is greater than 0.5, which means positive class, right? If output value is greater than, or output is greater than, uh, output probability is greater than 0.5, which means positive class, else negative class, right? So here in logistic regression, we will use this equation P hat or output is equal to sigma in bracket theta transpose x, right? So in output, we will predict probabilities. Any doubt in these equations? Okay. Yes. So if t is less than 0, if t is a negative value, which means the probability score you will get less than 0.5. If t is having any positive value, t is having positive value, which means the corresponding probability score will be greater than 0.5, right? So here you can say if theta transpose x means t value, right? So t is equal to theta transpose x we are taking here, right? This small t is equal to theta transpose x. Yeah. So here this theta transpose x we are taking as a small t, right? So when t is greater than 0, which means you can have any t value here, then the corresponding probability will have value greater than 0. So here probability will be greater than 0.5, right? Because this is the point where we are having probability 0.5, right? So when t is equal to 0, corresponding probability will be 0.5, right? And if you have any negative value for t, right? T is less than 0, then the corresponding probability will be less than 0.5, right? So this region we have negative values of t. This region we are having positive values of t, right? So if theta transpose x is positive, then we will have positive class, or label is 1. If theta transpose x is negative, which means negative class, or label is 0, right? So label 1 means positive class, label 0 means uh, negative class, right? So for the negative class, you can also here take 1 or minus 1, right? One, either you can take 1 0 or 1 minus 1, doesn't matter, right? Because in both cases we are solving a binary classification task, right? Okay, so any doubt in this example? Okay. Okay, so now let's discuss how can we train a logistic regression model, and what cost function we will use to train a logistic regression model, right? And yes, here we will use this equation to make the prediction, right? In case of linear regression, we will use theta transpose x to make the predictions, right? We will use theta transpose x to make the prediction. In logistic regression, we will use this equation. P hat is equal to sigma times theta transpose x, right? If P hat is greater than 0.5, which means positive class label 1, else label 0. Right? Yes. So here our objective is to find the optimal value of unknown parameter theta such that for the positive instances, for the positive class, we want high probability, and for the negative class, we want low probability, right? For positive class, what we want high probability, right? As you can see here, the probability is we are having a high value. So probability value is high for the positive class, probability value is low for the negative class. So that's what we want. We want high probability for positive class. We want low probability for the negative class, right? And
So
yes,
this logistic regression can only be used for classification, cannot be used for regression then?
no. We cannot use logistic regression for regression because here in output we are getting. So we have used some sort of threshold, right? So thresholding we are using here.
So
If
we can do only binary classification, is multimodal classifications are not possible?
yes. So multi-class also we can do here. So in fact, multi-class, what you can do for multi-class, you can use several binary classifier, right? So let's take one example. Suppose you want to solve a 3-class classification problem, right? So what you will do, you will train three classifier, right? So for class 1, you will train one classifier theta 1, let's say. For class 2, you will train another binary classifier theta 2. For class 3, you will train another binary classifier theta 3. Now, what this theta 1 will do? Theta 1 will predict whether the input belongs to C1 class or not, right? Positive, negative. Positive means input belongs to C1 class. Negative means input does not belongs to C1 class. Likewise, this theta classifier, theta binary classifier will predict positive, negative. Theta 3 also predict positive, negative, right? Now, for one input X, you will use these three models, theta 1, theta 2, theta 3. Using theta 1, you will make prediction for X. Theta 2, you will make prediction for X. Theta 3, you will make prediction for X. Now let's say if theta 2 is positive, theta 1 is negative, theta 3 is negative, which means X belongs to C2 class, because only for theta 2 you are getting positive score, right? Yes. So, and let's say if for theta 3 you are getting positive score, which means this X belongs to class 3, right? Okay, so now let me ask one question. So is it possible that for the same input, you are getting positive score for theta 1 and theta 2, for both, you are getting the positive score? Is it possible? Because let's say if here for theta 1, you are getting positive, which means input belongs to C1 class. If let's say if for model 2, theta 2, you are getting positive score, which means input belongs to C2 class. So is it possible that you can have a positive score for more than one classifier? Here theta 1 means model 1, theta 2 means model 2, theta 3 means model 3, right? Theta 1 is the parameter of model 1, using which you can predict whether a given input belongs to class C1 or not. So model 1 is a binary classifier. Model 2 is again a binary classifier to predict whether a given input belongs to class 2 or not, right?
Ideally, it should not.
Yes. Ideally, it should not, but it can be possible. Then what we will do in that case? We will take the maximum value, right? So for example, let's say here the maximum value you are getting 4. Here the maximum positive value you are getting, let's say 1. Then since in this case we are getting high positive value 4, then its class will be C1, right? If we are getting more than one positive score, then we will take the maximum score, right? Yes. So one method is to use multiple binary classifier to solve a multi-class classification problem. Other option is to use the softmax classifier, right? Or multi-normal. So softmax I will discuss later. So we have one extension of logistic regression that we can use to solve a multi-class classification problem, right? But yes, logistic regression we cannot use for multi-class classification problem, but we have extension of logistic regression that we can use to solve a multi-class classification problem, and that I will discuss after discussing logistic regression, right? Yes. Yes. So if we take this type of cost function, this cost function C theta satisfy both of these properties, right? What property we want here? We want high positive score for positive class and low probability score for the negative class. So if you take this type of cost function, it satisfies both these properties: high probability score for positive class, low probability score for the negative class, right? So here what exactly we are doing, we are taking a log function minus log p hat minus log 1 minus p hat. So if y is equal to 1, then minus log p hat. If y is equal to 0, y is equal to 0 means the negative class. Then we are taking minus log 1 minus p hat as a cost function, right? Okay, so now let's discuss the shape of log. So this is the function for log p hat, and this is the function for minus log 1 minus p hat, right? Because here we are taking minus log p hat and minus log 1 minus p hat is the cost function, right? If output is the positive label, if input belongs to the positive class, then we will take this is the log cost function. If input belongs to the negative class, or then we will take minus log 1 minus p hat as a cost function, right? Okay. So here x-axis we are writing positive or negative class information. Y-axis we are having cost function c theta, right? So y is equal to minus log p hat. So as you can see here, if input belongs to the positive class, if input belongs to positive class, which means y is equal to 1, then we will have here zero loss. Zero loss we will have here, right? If input belongs to the positive class, then loss is 0. But let's say if yes, so here what is this y? Y is the actual label. Y is the actual label, and this p hat is a model predicted right value, right? This p hat is a model predicted value. And what is this p hat? P hat is nothing but the sigmoid function of theta transpose x, right? Because what exactly here we are doing, we are learning, we are estimating optimal value of theta, right? This x is input, and this theta is the unknown value that we wish to estimate, right? So here we want optimal value of theta, right? Now using optimal value of theta, we can compute theta transpose x, and then we will take sigma function, right? And this sigma theta transpose x we are taking here as the predicted model predicted p hat, right? Now using this p hat, we will calculate these values: minus log p hat minus log 1 minus p hat, right? Okay. So if this minus log p hat value is let's say is a let's say or model is saying uh, negative class, but the actual is positive class, in that case error will be very high, right? Okay. Yes. So actual class is 1. Actually that sample belongs to the positive class, right? So actually that input sample belongs to the positive class. But let's say model is saying negative. Model is saying negative, which means if model is saying negative, which means p hat will be value, the output probability will be less than 0.5, right? If model is saying negative class, which means p hat or the output probability will be less than 0.5, right? Because for positive, p hat will be greater than 0.5, and for the negative, p hat will be less than 0.5, right? So if actually that point belongs to the positive class, but model is saying negative, which means p hat is less than 0.5. So if you compute this value minus log p hat, you will get a value here, right? Which means you will get a very high loss, right? So whenever we are having mismatch between the actual value and the model predicted value, we are taking a high loss, right? And if model is saying positive class and the input also the x also belongs to the positive class, which means whenever we are getting the same value, right? Model is also saying positive class and the actual class is also the positive class, then we will have a very low value for this term, right? Because this term we are taking as a cost function, right? So this value, and in fact, let's say if this p hat is 1, p hat is 1 means uh, very high confidence, with very high confidence model is saying class is positive, right? So for that, this cost function value will become perfectly 0, right? Because if you put here one value, log 1 is 0, right? Log 1 is 0. So this cost function value will become perfectly 0 when p hat is 1, right? And let's say if p hat is 0, p hat is 0, here I am discussing extreme cases, right? If p hat is 0 means 100 with 100% confidence model is saying class is negative, but actually the class is positive, right? So if p hat is 0, in that case we will have a infinite loss, right? Because if you extend this curve, this function, if you extend, then we will have a infinite value, right? So loss will be infinite if model is saying with 100% confidence that this sample belongs to the negative class, but actually the sample belongs to the positive class, right? So which means we can take minus log p hat as a cost function, right? Any doubt in this example? Right? If model is saying positive class and the actual class is also positive, then we will have very low value as a cost value, right?
Why there is a negative?
Yes, so negative we have taken because if you plot log p, the log p will be because since here we are taking p value in log function, and when value, so log x is negative when x is less than 1. So to make it positive, we have taken here negative. So negative is positive, right? Because in inside this log function we are using p hat, and p hat is a probability value, and probability always lies between 0 and 1, right? This probability cannot go beyond 1, right? So that's why if you put any negative value in the log function, the output will be negative. So to make it positive, here we are taking negative value. So negative will make it positive, so that we can have a positive log function, right? Any other doubt? Okay. Yes. So this probability p hat, you can also think whenever model is confident. So let's say if this p hat value is 1 or very high value you are having, which means model is highly confident that its class is positive. Likewise, if p hat is very small value, which means again model is highly confident then that its class is negative, right? So either we have a very high value for p hat or very low value for p hat, which means high probability or low probability model is confident that its class is positive or negative, right? So that's why here I have written high probabilities and low probabilities, right? Okay, so which means if actual the ground truth is positive, then we can use this function minus log p hat to add loss or cost to add loss if input does not belongs to the positive class, right? Because this minus log p will add positive value, will add some positive number, we will get some positive number if uh, if my input does not belongs to the positive class, right? And that number will increase as you decrease this probability, right? So if this p hat is 0, which means model is completely wrong. Model is predicting completely wrong that actually input belongs to the positive class, but model is saying with very high confidence, model is saying it's a negative class, which means very high value we will get as a cost function, right? Because here we are taking minus log p hat, right? Similarly, if actual output is negative, if input belongs to the negative class, right? If actual output is negative, then we will use this function minus log 1 minus p hat, right? Now this p hat remains the same, right? What is this p hat? Sigma theta transpose x is the p hat, which means this p hat is a probability, right? The only difference is for positive class we will get positive probability value greater than 0.5 we will get for positive class, and for the negative class we will get uh, this probability value as less than 0.5, right? For positive class we will have p hat is greater than 0.5, and for negative class p hat is less than 0.5, right? Okay, so this is the shape of 1 minus log 1 minus p hat, right? Y is equal to minus log 1 minus p hat. This is the shape of this function. Okay, so here the ground truth is 0. Y hat y is equal to 0, right? Which means the actual class of input is negative. Input belongs to the negative class, right? This is the ground truth. And if model is also saying model is also saying the negative class, right? Which means if model is saying negative class, which means p hat is a very small value. P hat you will get the output probability you will get a very small value, right? So if p hat is a very small value, 1 minus p hat will be a very high value, right? And we know log 1 is 0, which means in output you will get a very small number. So whenever the output is a negative class, model is also saying the negative class, in output we will get a very low number as a cost function. And if model is saying positive class but the input belongs to the negative class, then we will have a very high value here, right? So let's say actually the input belongs to the negative class, but model is saying positive. Model is saying positive with very high confidence, which means p hat will be a very high number. So let's say p hat is a 0.99. P hat is a 0.99, right? Which means model is saying with very high confidence that input belongs to the positive class, right? Which means p hat is a 0.99. So 1 minus 0.99 you will get a small value. So log small value you will get. So log 0 is infinite, right? Log 0 is infinite. So you can say here in output we will get a very high value, right? Any doubt here? Which means I can take these function to make my cost function, right? If y is equal to 1, I will use this function. If y is equal to 0, I will use this function, right? Because what finally I want if model is making mistakes, model is predicting wrong, then I want high value, high positive number as a cost function, right? So what I want this cost function to be small when model is making correct predictions, right? If model is making correct prediction, then I want this c theta value, this cost function I want is small. And if model is making mistakes, then I want this number to be big. And for that, I'm using these functions, right? Okay. Yes. Okay. So now what we will do, we will use uh, these two functions to make a cost function, right? Because here the problem is for y is equal to 1, we have one function. For y is equal to 0, we have another function. So now what we will do, we will make a combined function. We will make a combined function using these two functions, log p and log 1 minus p, right? And how can we make a combined function? The combined function is something like this, right? So this is the combined function where we are having log p as well as log 1 minus p, right? Right. So now I'm using both these functions log p and log 1 minus p to make a combined function as a and that combined function I'm taking as a cost function. So this function I will use to minimize the uh, uh, to minimize the cost, right? So optimal value I will get after minimizing this cost function. Yes. So as you can see here, we are using both log p function and both log 1 minus p function, right? Okay. Now to optimize this function, you can use any iterative method. Gradient descent you can use to optimize this function. So if you use iterative methods, iterative method will give you the optimal value of theta star optimal parameters it will give, for which this cost function j theta is as low as possible. And using that optimal value of theta star, you will make predictions, right? And for the prediction, what you will use? You will use the same equation, sigmoid uh, theta star transpose x, right? If this score is greater than 0.5, which means positive class. If less than 0.5, which means negative class, right? Okay. So here, let's discuss two cases. Let's say, okay, so here, what is this y? yi is nothing but the actual class for the ith input, right? So this yi is the actual class for ith input. So let's discuss here two cases. Suppose actual class is 1, but model is predicting negative, right? So actual class is, let's say, positive, but model is predicting negative. So let's say model prediction is negative, but the actual class is let's say positive, right? Okay, so if actual class is positive, which means y is equal to 1. And if model is predicting negative with very high confidence, which means this p hat must be less than 0.5, right? So assume p hat is equal to 0 for the sake of simplicity, right? Because if model is predicting negative, which means the output probability has to be less than 0.5, and in this extreme case it can be 0, right? Because if probability has to be very, very small if for the negative class, right? Then we can say that with very high confidence model is predicting negative class, right? Okay. So if you put here 1 and 0, which means model is making mistake. Model is making mistake, right? Actually, input belongs to the positive class, but model is saying negative. So if you put here 1, and what is log 0? Log 0 is infinite, right? So if you put here 1, then log 0, then here what I will write plus 1 minus 1, right? 1 minus 1, and then log 1. So log 1 is 0. So the second term is 0, right? And here, since we are having log 0, so log 0 means infinite. So infinite value you will get, or very high value you will get here, which means if there is mismatch, you will get a very high value. Now, let's discuss other case, other side. Let's say if input belongs to the negative, actually input belongs to the negative class, which means y is equal to 0, which means ground truth is 0. Ground truth is 0 means actually the input belongs to the negative class, but model is saying opposite. With very high confidence, model is saying positive class, which means p hat is 1. So if you put these values, again you will get a very high value for loss, right? So if you put here y is equal to 0, so if you put here y is equal to 0, the first term will vanish, plus the second term, what value you will get? 1 minus y hat is 0, then log, here if you write 1, log 1 minus 1 is 0. So again log 0 is infinite, so you will get a very high value. So very high value you will get when there is a mismatch between the actual value and the model predicted value, right? So whenever the actual label is 1 and model is saying whenever the actual label is positive but the model is saying negative, or